Hey Doug, how's it going? Hopefully you're doing well. I just saw your post on Facebook maybe an hour and a half ago or something, asking for some advice on, I guess, FEA on some I-beams that you're going to make davits out of for holding up your tender on your boat. And you're just asking about the loading constraint or the loading situation and failure analysis of that system. So I thought I'd give you a hand here. For those of you who don't know me, my name's Lau Kaczynski, and I'm studying mechanical engineering at San Jose State University, and I'm in my final year. I am concentrating in mechatronics, so I'm not super familiar with failure analysis of mechanical systems, but I definitely have taken a couple classes in the subject. It's been a little while, but I know there's a bunch of people that watch your stuff, so I'm sure they'll be more than happy to check my work. Without further ado, let's get into it. So what I did first is just looked up the I-beam that you were talking about on Google and found this little cross section here of I-beams, and you were talking about the W4 times 13 I-beam. Hopefully I said that correct and didn't sound like a dumbass. But anyway, here's the little legend and the drawing and all the little variables on it. So here's all the dimensions in inches for the I-beam. So what I did is pulled up SolidWorks, which you can grab a copy of if you just lie and say you're a student. You can download a free copy and do this analysis yourself. But I just grabbed the sketch here and sketched out the I-beam. So we have a 4.06 wide, 4.16 tall, and 0.35 and 0.28 all in inches dimensioned I-beam as the little thing on Google dictated. So once I did that, I just threw in a little fillet in the corner to try to match a little bit more the I-beam as you'll get it from your metal shop or wherever you get your material. I went ahead and extruded that 3 feet like you were talking about. Let's just verify that real quick. Yeah, 36 inches. So that's the I-beam there that you're talking about, hopefully. And we go ahead and do a simulation of this. Try to keep this short because I know you don't like to get that involved with the engineering stuff. But just for your reference, this model or this analysis I did with aluminum 6061 T6, and then I did another one with steel to compare. The steel one was 1020 steel cold rolled, which I'm not that familiar with the different steel alloys, but hopefully that's similar to one that you maybe consider using. I think you mentioned going with steel. But anyway, for the loading situation, I made this face universally constrained. So what that means is that this beam for our analysis is imagine this face of the beam, this end, is just stuck to a surface here, the universal surface, and you can think about that as like welded, all the way around, but including the attachment of the middle, the center parts of the I-beam. So like a perfect weld where you have perfect penetration, stuff like that. And then I have the loading, the force loading on the end here, 3,000 pounds on the very farthest face here, going straight down, and yeah, it's a pretty easy analysis as far as analysis goes, but I went ahead and ran that. Once again, for the people that don't know the situation, is that Doug wanted to make 2 davits and have a tender hanging from underneath. The tender's 6,000 pounds, and since there'll be 2 davits, it's 3,000 pounds per davit is going to be what's hanging on here. So let's go ahead and look at the stress analysis. What we're looking at here is a image of the model that's color-coded with the legend over here. And underneath the legend, you'll have your yield strength, and the legend is the von Mises stress. So what the von Mises stress is all your loading for each individual piece or nugget. You can think about it, a little tiny piece of aluminum or piece of this I-beam. you're doing analysis for each little tiny sector, and you're calculating all the stresses for that sector. So that's going to be stuff like your bending stress and your shear stress and stuff like that. The von Mises stress is a nice little calculation that takes into account all the stresses and then lets you reference that to the yield strength, and the yield strength is a material property. So for our two analysis, the two analysis that we did, we'll see the same graph because our loading conditions are all going to be the same. We'll see the same legend too, but what will be different is where the yield strength lies, and that'll tell us what our safety factor is. So I'm not sure if this helps you that much, because the question you were really asking was in regards to this like calculator you found online for stuff like this. I'm not really sure how to answer that question because I couldn't really see the full details of the page you were looking at. If you want to send that to me, I can give you my 2 cents. But this should give you a good idea of what's going on in your mind. So anyway, looking at this situation, imagine, first you want to look at the results from far away, hypothetically speaking, and you want to make sure that the results make sense. So what we're seeing here is our loading is over here. We're not seeing much stress because we're in the blue region, right? The lower region of the von Mises stress. And then as we get to the left side, we're getting to the green, and maybe at the end we're getting some red. So we're seeing a lot more stress on the left-hand side, right? Now this makes sense because think about it like this. If you have your car and you're trying to undo a lug nut, and this is a breaker bar, and you have your lug nut on this end, and you're leaning or standing on your breaker bar over here. If this system's going to fail, your lug nut and your breaker bar, where is it going to fail? Well, it's certainly not going to break the handle off of your breaker bar where you're standing, right? It's going to break either the connection between your breaker bar and the socket, or maybe the socket will break, or maybe the lug nut itself will break. The stud in your car will break off or shear off or whatever. All your failures are going to be on the left hand side, so that's where you're going to see, or that's where we're going to expect to see the failure point, and that makes sense here, right? Same condition. So let's go ahead and zoom in. We can see we have a very red region here on this pointy section of the I-beam, which makes sense as well. Anytime you're doing stress analysis, if there's a feature that's pointy, it's going to concentrate stress at that point, and that's where your failure is going to occur first. So that makes sense there. What we want to do when we're looking at this is find, make sure that the stress concentrations make sense, and then reference that point with respect to the yield strength, and the ratio of those will give us our safety factor. So what we're doing here is looking at a real red region, right? So we can call that the von Mises stress at the top, which is 1.85 newtons per meter squared von Mises stress. And then we can look at our yield strength, which is 2.75 times 10 to the 8th newtons per meter squared. And all we have to do is a quick little ratio of the two. We're just going to divide the yield strength by the von Mises stress. So we have the yield strength listed at the bottom there, the legend, which is 2.75, and we're going to divide that by the maximum observed von Mises stress, which is red, so we'll call it 1.85. 1.85. So we get about 1.5. So that is not a very good safety factor. You definitely want safety factors higher than 1.5 for systems that could hurt you if they fail, and stuff like that, stuff that's supporting humans or whatever. For your boat, you definitely want something bigger than that, because you don't want it to fail while you're out at sea and cause you a big problem. But what's good about this situation is that when you're building this, you're as an experienced builder, you're certainly not going to just weld this end of the I-beam to the side of your boat and try to hang your tender off the side of it. what our calculations are telling us is that would work, but our safety factor is very small. What you're going to do, because you have experience building stuff, is you're going to put a gusset or something, either underneath or on top, and that's going to dramatically increase your safety factor and dramatically increase the amount of weight that the system can hold. Let's look at the steel representation real quick, just to give you another perspective with the steel. So same graph, right? Everything looks the same, except for our yield strength is now 2.5. What was it before? I've forgotten already. 2 point something? Yeah, 2.7. 2.7, and with steel we got 3.5. So we can do the division again real quick. 3.50 divided by 1.82. So we got almost a safety factor of 2. So steel is definitely going to help you out and would be a better choice for this application. But like I was saying, what you're really going to want to do is put a gusset on the bottom or on the top to increase the amount of weight that your system can hold. So for example, if you were able to put your gusset from the center, 45 down, something like that, we can go ahead and do the same division, but instead of using the von Mises stress of 1.82, where we see our maximum failure point over here, we can say it's somewhere in this turquoise region, somewhere between the blue and the green, which, from our legend we can see is 4.67 times 10 to the 7th instead of 10 to the 8th, which is our yield strength. So let's go ahead and do that again. So that's 335 divided by, let's give it, let's say about 4.6. Okay, so now we're talking. Now we have a safety factor of 7.6. So, that's still not crazy high. That's much better. It'd be good to get that up. I would say like 10 or 12 or something like that. But you probably it sounds like you gave me some extra load in there when you gave me the constraints. You said that the boat was filled with water from a rogue wave or something like that. Your tender was filled with water from a rogue wave. So it sounds like you gave me a weight that was already had some extra mass thrown in there. But yeah, use your best judgment. You're definitely on the right path here if you get some good gussets going, and you exaggerated the weight of the tender. You said 3 tons is what we were using here for the 2 gussets. So yeah, it would be nice to increase the size of this I-beam, but if you get a good gusset out there on the top, something like that, it should be doable. If you have any other questions, let me know. But yeah, hopefully that gave you a little bit better of an understanding of what's going on with that situation. And let me know if you need more help. Thanks. Have a good one. Bye.